Okay, so we'll continue on with the discussion of conformational analysis. So remember that the definition of a conformer is a conformational isomer. So the rotations about sigma bonds lead to different conformations. And so as we move forward, we're going to use these words conformation and configuration, and they mean different things. So today we're talking about rotations, and we had left off on ethane last time, where the red and the blue were hydrogens. And now we're going to go through propane and butane, so the two left molecules there, where we imagine that the blue and red spheres are substituted for different groups. So we'll do those in class. There's a couple examples you can do on your own. And then we're going to get into cycloalkanes. So they have a different type of strain. So when we talk about rotation, there's a strain or energy penalty induced. So we were looking at sort of the perspective where the carbon backbone is in the plane of the projector, and the Newman projection, we're looking down an axis. So that would be a staggered conformer. And because that carbon-carbon sigma bond can rotate, the stagger becomes eclipsed. And so eclipsing is a form of strain. And what that means is there needs to be energy put into the system to overcome that strain. And as we move forward with learning reactions, we'll see that a lot of things are driven by strain. So this is one form of strain. So we're going to pretend now that this blue one is a methyl group. And then we'll go through the rotations and see how the energy differs compared to ethane when it's hydrogen. I don't see any model kits out in the crowd, so we'll just draw some stuff here. So when you're reading these questions, it's always going to give you a perspective. So C1 to C2, we want to put C1 in front and then C2 in back. And again, the Newman projection will change based on how that is designated. So let's just go ahead and draw this out, and we'll do one rotation and see what the penalty of that is. So there's our eyeball, and we're looking down that sigma bond. So the front carbon 1 has 3 hydrogen substituents. So that's the front carbon, the 3 hydrogens. Now the back carbon is represented by a circle, and then it's going to have 3 substituents sprouting out from the edge of that circle. So we have 2 of them will be hydrogen. And now the third one is going to be the methyl group. So that's a staggered conformation. And I think last time I was holding the back carbon constant. So I'm going to rotate the front carbon. I'll do it clockwise, 60 degrees at a time. So I'm going to keep that back carbon the same. And now that conformer is called eclipsed. So you'll notice there's 3 eclipsing interactions, and what we have to do is go up to the table here, see what each of them are, then add them together, and that gets our total strain for that conformer. So we have HH, so that would be +4. Then we have methyl H, so that's +6, and then a second HH. And so that would get us 14 kilojoules per mole. Then if you repeated that 60-degree rotation, you'd end up with a staggered, and relatively speaking, we would set that energy to 0. So the eclipsed is plus 14 kilojoules per mole higher in energy. And those are really the only 2 conformers you can draw for this, because you're either going to get staggered or eclipsed. But as you change the substituents on the carbon chain, as we'll see with butane, you're not always going to end up with this sort of 1-2 staggered conformers. You'll end up with different ones. So when we plot that, the staggered we're calling a relative energy of 0. And then when it goes up to eclipsed, we've added the 3 eclipsing interactions to get 14. Then it just continues the rotation in that sine curve pattern. So as I mentioned, the nature of the bond you're looking down will matter. And then as we get to butane and then higher hydrocarbons that are linear and branched, we're going to end up with more conformers, and therefore the curves won't look, this simple. Any questions? So now we're going to use the same sort of deal where in that model on the table, both the red and the blue spheres are now both methyl. So that's going to be butane. And it says we want to look down C2 to C3. So that's sigma bond now. As I said, with these normal sort of zigzag drawings where the carbon backbone is in the plane, one thing we can sort of clue into, if our eye is looking at that and we want to transfer it into a Newman projection, carbon 1 is going to be down. And then on the back carbon 3, carbon 4 is going to be up. So I want to orient the Newman projection that way so that we can get things sort of settled, that when we start doing these rotations, we'll see the different conformers. So if carbon 1 is down, I want to have a bond pointing down. That means I have to draw like this Y, and those 2 substituents are going to be H. So the back carbon 4 has to be up. And the other two substituents are H. So depending on how you visualize that, if you kind of just rotate this a little, that might help you visualize how you change your perspective and start drawing the Newman. So we're going to use some more terms here based on the dihedral angle. And these terms are really when you define two substituents, what their relationship to one another is. So we're looking down C2 to C3. And I want to focus on the methyl group here and here. So the dihedral angle between them now is what? So 180. So another word that we use for that is anti. So that's one conformer and it's staggered. Maybe take a minute or two to think about, if you keep the back carbon the same and rotate the front, how many unique conformers can you come up with? Or just page ahead on the slides and you'll see the answer. You're going to keep the back the same and then rotate the front. So these rotations are always done in 60-degree increments. What? Yes. So we have one drawn, so it's got to be more than one. If you do a 60-degree rotation, that's going to get you at least two. But then how many more after that are there? A way to figure this out, again, using those two methyl groups is sort of what you're focusing on. How does their relationship change to one another? Any guesses? So it's 4. So we have 4 unique conformers. We should have 2 staggered and then 2 eclipsed. I'll run through the drawings on the next slide, but say I want this methyl group. This is the C1 methyl group that's down. This is the C4 methyl group that's up. So that's staggered. And then rotate this way for you guys. So now there's eclipse. So that's unique. Now pay attention to the dihedral angle of 180. So now it's collapsing. It's getting smaller. So that's another one. That's staggered. That's unique. Because the dihedral angle between the methyls is now 60. And then the final one is eclipsed. what is the dihedral angle between the two methyls now? So it's 0. So at 180, that's called anti. At 0, that's called syn. So 180 and 0 are both in the same plane, but they have different angles. So 180, 180, and then 0. So the 0 is syn. So the reason that will come back to haunt us later on, just generalize the red and blue to different substituents. And if we're looking at sort of describing the space of a molecule, we can say there's sort of a top and the bottom. So here, those two substituents are on the top face, the same. Now here, you have one on top, one on bottom that's anti. And that will relate to some mechanisms that we'll learn later on. How do you define the relationship between those two substituents? So with the butane, we now have 4. And so each of them is going to have its own unique strain associated with it. So we have staggered, and then considering the methyl groups, that was the anti-conformer. And when we look at the interactions on the table there, we don't see any eclipsings at this point, so we could say the relative energy for that's going to be 0. Yeah, so I'll explain what that one is because it's special. So now we've done a rotation, and so we're eclipsed. We have 3 interactions. We go to the table to see how much each one costs. So we have HH, that's +4. Then we have methyl H, that's +6. And then we have another methyl H, that's another +6. So that would get us +16. So right now, of the 2 conformers, it kind of resembles ethane and propane in the sense that, you know, you're 0 and then you have this high one. But then as we continue to rotate, the other 2 are going to have different energy values. So you're not going to have that nice sine-looking curve anymore. So we're back to a staggered. Yeah, and so far we've seen with staggered, there's no penalties, but this one is unique because that dihedral angle between the 2 methyl groups is 60 degrees. And that's called a gauche interaction. Gauche means something in French of which I do not remember. Left means left. How that translates to this, I'm not sure. But so that is +3.8. And again, that's only for a methyl gauche. So even though it's staggered, it's not the lowest energy staggered conformer. And then we do one more rotation to get the 4th unique conformer. And you can see from the energy penalty table, that one's going to have a methyl eclipsing. So that's one of the bigger ones here. So we're back to eclipsed. We have the 1, 2, 3 interactions. We go to the table. to define them, grab the energy values. So we have HH, HH, and then methyl, methyl. And so that's going to get us to plus 19. So that's the highest of the four. And then as you continue rotating, what you're going to do is just make one of these other ones you've already figured out. And so the curve kind of looks the same after that. So up above here, these are the rotations in the squares. Then below, we've plotted their energy. So we go from staggered to eclipsed, staggered, eclipsed. And then after that, you're just repeating those conformers again. So 0 up to 16. And then again, because of that gauche interaction, we don't go all the way back down to 0. Then we have the methyl eclipsing. That's the highest at 19. So a couple things I want to point out about this. For terminology we're going to use moving forward. Our x-axis here is that rotation about the sigma bond measured through the dihedral angle, and the y-axis is that relative energy. So of the four, remember we said there were 2 staggered and then 2 eclipsed. Based on the chart that we see, we would say plus 19 is the global maximum. And then 0 is the global minimum. And then between that, you have these local maximum, local minimum. Now, granted, for butane, you only have like a local max and a local min, but as you start sprouting substituents off the carbon chain, you can get a lot more little peaks and valleys between that stuff. So nowadays, most of this is done with computer software. You draw the model in there and you make it rotate and it'll plot this stuff out. One thing I do want to raise your attention to is this graph is like a slice in the three-dimensional energy space. What I mean by that is, like, if you took a mountain range and kind of sliced it in half, this hill is 3 dimensions. And so I'll very crappily draw this in. So you can imagine there's this, you can walk around that hill. Then down here, you have this valley. And so these kind of things are called saddle points, like a horse saddle. We won't get too much into that, but we will need to study energies of reactions moving forward. And for the most part, we're going to look at these kind of 2-dimensional slices of a 3-dimensional space. And the reason these things are 3D is, if we recall back to IR, when a bond stretches, and the signal in IR has a width, the width is due to these quantum states of how much that bond can move. So when these things rotate, they can rotate infinitely, but it's done to a quantum manner. And so that's best represented through a 3D
graph, but we're just looking at really the max and min, whether it's global or local. And so, yeah.
At some point, are we going to have to use this conformation analysis to determine the molecule?
Yeah, so that was the point I was going to bring up next. So why are we studying this? Because these sigma bonds rotate, what you're seeing is it's the same molecule but in different conformers. So when we learn reactions, we would say of those four, the anti is the most stable because it doesn't have strength. But of the four adding to 100%, you could say, well, maybe this is 80% of the time it's like this, and then 5% of the time it's like that. 0.5, this population of these conformers. So even though the molecule is most stable like that, perhaps it is not the reactive conformer. Maybe the reactive conformer is like that. But since that is not populated a lot, how do you get the reaction to go? So it exists in this, then it can proceed. So as we move forward in this module and the next one, we're going to start talking about that Arrhenius equation with heat, where if you change the heat, you can increase the reaction rate. And so really what heat is doing is allowing you to overcome the strain. Because things don't want to exist like this, but you have to get it in that conformer. You have to alter some of the variables. So what you can do on your own to practice this, there's a couple molecules listed. I'll draw them out. And then if you've gone through those different carbon count constitutional isomers with practicing naming, you can do the same activities. And then just look down different bonds. So we did propane. What about 2-methylpropane? So looking down the 1 to 2 bond, (2-methylbutane), looking down 2 to 3, (2,3-dimethylbutane), looking down 2 to 3 as well. And then, as I said, as you sprout other substituents off the carbon backbone, you look down different bonds, they're going to be different Newman projections. And as you go through that exercise, you do those rotations, go back to that table, assign the penalties for that, and then try to plot out one of those graphs. So through the sigma bond rotation, there's strain induced, again, primarily through eclipsing interactions, but then we've seen this staggered one with gauche. What I want to move on to now is looking at cycloalkanes. They have a different type of strain, and this is given the sort of organic name, Bayer strain, or Bayer, however you want to pronounce it. So the reason that we're doing this connected to the acyclic. So acyclic, there's no ring. The sigma bonds rotate. When we move into a cyclic system, the terminal carbons have been linked together. And so you're limiting the degrees of freedom. But also based on that, depending on the ring size, you're going to introduce another form of strain. That's called angle strain. So to a certain extent, there's a limited type of rotation in rings. We call it another term. But the angle strain and then this other type of rotation lead to a different type of conformational analysis. So to preface this concept of strain, how do we measure it? So getting back to this thing of, there's this relative energy of conformers that's the lowest. Then some rotations happen and the energy goes up in that strain. So of all these, different molecules and functional classes, how do we know that something has strain? So we're going to use the heat of combustion equation to calibrate acyclic hydrocarbons relative to cyclic ones. And then through the differences, we can start defining these different types of strain. So that a heat of combustion equation is shown here. So basically you take your hydrocarbon plus some oxygen, a spark. That generates CO2, water, and then this N here, that's what we measure as heat. So you may have done something like this, maybe not exactly combustion, but like calorimetry. In Gen Chem, it's conceptually simpler, conceptually analogous, where you're measuring the change in temperature. And then that you shove that back into some equations, and then you can start calibrating. So let's look at this table here where we're starting with an acyclic hydrocarbon. And we'll use the most general case of a linear one. We know that for an sp3 hybridized carbon, an HCH bond angle is 109.5. It's the normal bond angle. So I'll explain a little bit more about what compression means. But since it's the normal hybridization, we're going to say that is 0. Depending on what N is in this equation, you basically average out to about 658.6 kilojoules per mole per CH2 group contained in that molecule. So that's what it should be for any N number of carbons. That's the normal thing without strain. Now the rest of the cases, we're going to look at cycloalkanes, starting with the 3-carbon one, cyclopropane, then going up to 8 cyclooctane. So if we draw cyclopropane, there's our equilateral triangle. There's 3 CH2 groups. So the internal CCC angle is 60 degrees. So for any triangle, the internal angles have to equal 180. So why is this number here in red? So your normal sp3, like H, carbon H, that's 109. In a ring, the carbon-carbon angle you're taking that natural thing and you're doing that. So you're compressing that to a smaller angle. And I haven't hit the gym in 8 years or whatever, but you do the pec deck, you know what I'm talking about? You squeeze. So what are you doing there? You're putting strain here, right? And you feel it. It's the same thing. That angle is feeling that strain. So what wants to happen? It wants to go back like that. So strain is equal to reactivity. So the more of that's in there, the more reactive it is. So if we go through the rest of that row and compare it to the acyclic case, we'll see there's some big differences. So the difference between 109.5 and 60, it's been compressed to a smaller angle. When we take cyclopropane and run it through the heat of combustion, it's giving off that total amount, 2091 kilojoules per mole. So I've taken this number and divided it by 3. So in the next column, I'm taking that number and subtracting it for 3 carbons, what it should be without strain. And I get 38.5. And because there's 3 of those CH2 groups, I just multiply that now by 3. And what falls out of that is the total ring strain. And that's that term Bayer angle strain. That's due to the compression of the normal hybridization bond angle. So nowadays, people study this in research. It's strain release reactions. So if you follow that logic down for C4, C5, you'll see they're still in red. But this case here that's in green is cyclohexane. So the 6-carbon ring, for the most part, the values you see in this row resemble what you see for an acyclic system. So as the ring gets larger to the C6 carbon count, it most resembles an acyclic system, meaning there's no angle strain.
Why did you divide and multiply by 3?
So basically, you're normalizing this per CH2 group. And then from that to get the total angle strain, so whatever N is, that's what you're going to multiply there. So this is kind of the low point in terms of strain. As you go back up in carbon count from 7 to 8, you see the strain start creeping back in. And there's other sort of reasons why that is. When rings get bigger and bigger, again, it's kind of like a ball of yarn almost. These things start tangling back on one another, and that's another form of strain. So small rings have a lot. 6 is the normal, and as you get to bigger rings, there's other sort of interactions happening that start pumping that number back up. So because the 6 one resembles the acyclic, we're going to focus on that primarily. to finish off this part of the module. And something that is interesting about the six-membered ring is we see it quite a bit in nature. So the scientific investigation over human history has kind of aligned with what nature produces. So we'll see six-membered rings in carbohydrates, in DNA, and you can kind of rationalize why that is based on these arguments. So there's cyclohexane. It's C6H12. There's 1 degree of unsaturation, that's the ring. And again, what is challenging about organic is, as this is drawn, it looks flat, meaning that all of the carbons lie in the plane of that projection screen. But since we know that sp3 hybridized carbon is tetrahedral, each of those carbons has 2 hydrogens. And then what is kind of a lie about drawing it like that is those H's can't be in the same plane. So if we put some H's coming out, some H's going away, we see that some are towards you, some are back. So that's further complicated. As I said, the carbons are not in the same plane. And so that's going to render these H's different. So the structures that you see here on the bottom were ripped from a paper by Derek Barton, who first described this stuff, and along with another scientist, Odd Hossel, won a Nobel Prize for figuring this out. In their initial description of these things, you see on the left here it says P. On the right it says E. So nowadays we don't use the term P. We use A or axial. But of those 12 hydrogens, they're now grouped into 2 classes, axial or equatorial. So axial hydrogens, for lack of a better way of saying this, are kind of up or down. And equatorial are along the equator of the carbon backbone. It says E, but it can be anything. Yeah. So now that we've looked at converting something flat into this kind of 3D shape, I want to explain a little bit more about that and how you go about, looking at these flat things and drawing them in this form, and then helping you visualize the implications of that. So as I mentioned, these 6-membered rings are seen in a lot of naturally occurring compounds. And so the one that is shown here is cholesterol. And cholesterol has a steroid nucleus. So steroids typically have those 4 rings. On the left, I've drawn it flat, and on the right, I've converted it into this other thing where we can now see what is axial and equatorial. So your body makes cholesterol. I mean, typically when you're watching, TV, they're saying don't eat cholesterol-rich foods, blah blah blah. But you do get it from food, but your body also makes it. So it's made in 37 chemical steps, and it's a component of cell membranes. And so cholesterol is the starting material for other hormones such as bile acid and vitamin D. So 37 steps, that's not the pace at which you or I operate in the lab. It happens pretty quick. And so that is controlled by enzymes. So what I want to focus on is helping you understand, see that secondary alcohol, how that bond is like a wedge or it's out towards you. When you convert that ring into this, why did I draw it equatorial? So we'll start off with, drawing these things and then looking at the substituent go axial or equatorial. So how do we draw a chair? So you start off with kind of two offset parallel lines. The thing to remember is everything has to be parallel to something else. That's how you end up with the symmetric chair. So now I'm going to draw in this bond, which is parallel to that bond. And then finally, I'm just going to connect them. So that's called a chair. And then as you see, in a chair, there's two conformers. So the main thing is opposing bonds should be parallel. So I would say, you can practice that. We'll do some more of these drawings in a little bit. So how does that make two different types of hydrogen? So here's a six-membered ring. The purple ones will mimic the blue ones up there. The yellow ones, think of them as the red. So there's two classes of hydrogen now based on this chair conformation. So the blue ones are axial. So how many axial hydrogens are there? There's 6. And so when we start talking about sort of the geography of a molecule, we can use some terms that we know. So here is the top side. So of those 6, there's 3 on top and then 3 on bottom. Then the yellow ones here, the red ones up there, those are the equatorial ones. So notice that they're kind of along the equator. And when I talk about these, I'm going to slice the molecule in half with where my arm is holding it. So I have 3 equatorial to the right, and then 3 to the left. So at no point when you're drawing a chair should any of these bonds be drawn into the ring. That's more of an art thing, but I think it does reflect on how you understand the visualization. So we have the top, the bottom, the right, the left. And then of those quadrants or octants or whatever, you can specify specific height. So this is one conformation. How do we get to the other chair conformation? In my right hand, I have a carbon that is up. In my left hand, a carbon that is down. So I'm going to flip them, and I'll do it stepwise. So the right one, I'm going to flip down, the left one up. But notice the colors of the hydrogens. So the blues are all axial. So I've done one flip. And so this is a different conformer now. This is called a boat. Maybe it looks better like that on a boat. I'm on a boat. So when I flip this one up, notice the change in hydrogens. So these yellow ones are now axial, the blue ones are now equatorial. And I know you're thinking, well, whoopie shit, what does that have to do with anything? In learning organic chemistry, we're always looking to generalize every concept. So if we're going to take hydrogens and start substituting, we substitute an H for something else, and then what if we put on 2 substituents? What's the relationship numerically? Is it 1, 2, 1, 3, or 1, 4? And then of that, which chair flip is the most stable? So when we were talking about acyclic conformers having 2, 3, or 4, which one's the most optimal? We're going to do the same thing with these chairs. So again, I always try to orient yourself, the top, the bottom, the left, the right. As I said, the axial bonds, as you draw them, should always be parallel to one another. The equatorial bonds, so I'm gonna slice right here. You see how these 3 to the right, they point to the right. The 3 to the left point to the left. So what you don't want to do or visualize is draw a hydrogen like that. That's pointing into the ring, so that's bad. But also, again, it's no longer pointing to the right. It's pointing to the left. So if you're able to classify those, it'll make the downstream analysis a little bit more straightforward. So there's 3 main conformers. You have the chair, then this intermediate boat, that's high energy. And then finally, you get to the other chair. And so the boat has a penalty of plus 45 kilojoules per mole. So between those three, there's other little things that can exist. We're not going to get too much into the nuance, but so if I take this, so there's the boat. When the opposing 1 and 4 carbons are kind of eclipsing one another. So between chair and boat, there's this thing where it's flat. It's called like a half chair. So that's another conformer. We're not going to talk too much about those things. So we're mainly just going to focus on the 2 chairs that you can draw. So there's some pictures that I took of the model kit that I use. So from the perspective of the drawing to there, that's the same. And then below that is just a Newman projection. So this is called like a double barrel Newman projection. If I use some highlighting here, say that blue carbon is that one, and then this green carbon is that one. You can draw Newman projections of these as well. Any questions? So bada bing, bada boom, that's cyclohexane. You flip it, the substituents are all hydrogen, so it's not terribly interesting. So let's start substituting a hydrogen for something else. So these are mono-substituted. So I can just call that, say, some group R. And then the 2 chair conformers are shown for methyl cyclohexane. So notice what happens when you substitute one of those. Now the red one is the methyl. So the methyl group here is equatorial. Then when we flip it, it's axial. So this can be pretty much anything. And again, that's not the most terribly interesting thing in the world, because whatever that is, you're just going to draw it. It can be chlorine, bromine, ethyl, or whatever. But how does the nature of this group affect which one of these is most popular? So the 2 chairs, where the group is equatorial versus axial, which one of those conformations exists? It has the lowest strength. So in general, substituents that are equatorial are more stable. When you do the ring flip and you make it axial, what is the issue now? So this group is going to change in size. And I said these axial bonds are parallel, right? And so now you have what's called 1,3 diaxial interaction. So these hydrogens, they feel the size of that group when it's axial. And so what does that mean? It kind of wants to get away from it. So in general, you want the substituent equatorial. If we expand that, for any ring, you want as many substituents equatorial as you can get. So when you do these problems, you have to absolutely draw both chair conformers and then determine which one has the maximum number of equatorial groups. So the size of the substituent for organic chemistry, the word that we use is sterics. So we would say steric hindrance. So what is the nature of that group X or R, where we have the equatorial versus axial? So there's X, these different functional groups you've learned. What does this mean in the middle here, this delta G? It's basically saying that for fluorine, the axial conformer is 0.8 kilojoules per mole higher in energy. Yeah, axial is higher. The reason I drew this line here between the acid and the methyl, as we'll see in these pictures here. So we're going from methyl, then we're going to substitute an H for a carbon to make ethyl, do another one isopropyl, and then another one tert-butyl. So that central carbon there that's the carbon that is bonded to the ring, and then you have these groups sprouting out from it. You'll notice that for methyl and ethyl, they're kind of the same. Isopropyl, it bumps up a bit, but then tert-butyl is really big. This last column here, delta G, you're just taking this number and subtracting it from the 7.6. So why is that tert-butyl so high? So here's now our methyl group. It's equatorial. When we flip it, it's now axial. And so, as I said, the size increases. So there's this 1,3 strain. So that's looking at the ring substituent. If I rotate it, and now we're going to look down this bond, this carbon-carbon signal bond. So like this, and then consider what these things are. So if these are all H, kind of the same size, it doesn't matter what the Newman projection is. But then say we take one off, we replace it with now a methyl. So this is the ethyl group, and that's bigger. You wouldn't want to rotate that into the ring, because now there's a lot of strain. But it can put this out so it's staggered. And then we do another methyl substitution. The balls are falling off the table here. But these can still go out. But then the last one, maybe I'll just put this on here to show you that it's a methyl group. So methyl, methyl, methyl. This one has nowhere to go. It doesn't matter how you rotate it, there's still a methyl group in the ring. And so the size of that is what makes that axial one the most strain conformer. So the bigger that group is, the more it wants to sit equatorial. And so in designing syntheses, you can take that into consideration to bias a substrate. So again, we're looking down the carbon-carbon bond, seeing what is put inside the ring. So H, 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 and then here it's methyl. And so that explains why this increases so much. So regardless of what that substituent is, if it's only one substituent, you have the axial versus equatorial. You kind of look at this table to see what's the preferred one based on the energy difference. So this is where we're all going to earn our paycheck here. What if there's two substituents? So not only do we have to specify the relationship between them, so are they right next to each other, 1, 2, or are they 1, 3, or 1, 4? So there's that position.
It can't be 1, 1, 2, 2, 1.
You can have 1, 1. I suppose that would be another case. And then you'd have to look at the size of each to determine which one is going to be equatorial versus axial. So the thing now is, so there's the positional relationship, but then I have these other terms in here, cis and trans. So cis means same, trans means opposite. So when I was talking about the face, top or bottom, the cis substituents are going to be on the same face. The trans are going to be on opposite faces. So then for each one of these, you can draw those chairs and then determine which conformer is going to be the most stable or strain-free, how you want to think about it. So let's do some examples here. So we'll start with the cis 1,2-dimethylcyclohexane. So there it is, flat. I've shown the positional relationship 1, 2. Now let me show cis. And for that, I'm going to use these wedges. So that means they're on the same face. So I'll put some numbers in here because I said they were 1, 2. I'll say 1 is right there and 2 is right there. So the methyl group on carbon 1, am I going to draw that axial or equatorial? What? So that, remember, the wedges are coming out towards you. So you're, again, looking at this at a 90-degree angle. But if you take your eyeball, kind of swing it around this way and then look up, you'll see that those methyl groups are kind of up. And so when I translate that into the chair, they have to be up. So up at C1 is going to be equatorial. And so because they're cis, the methyl group at C2 should be what? Axial. So I did a chair flip. So this becomes 1, that becomes 2. So basically you're just flipping everything. Carbon 1 was equatorial, so now it has to be axial. Carbon 2, methyl was axial, now it has to be equatorial. Notice that both substituents are still up. So let's do the trans. We'll keep kind of those things the same so I don't lead us too far into the forest here. So the carbon 1, it's still up. Carbon 2 is down. So that means that methyl group is going to be equatorial on top. Now the methyl group at C2 has to face the bottom, so it's got to be on the opposite face, which means it's going to be equatorial. Then when we ring flip that, they're both axial. So with the cis one, you'll notice, since both substituents are methyl, you have one equatorial, one axial, one equatorial. So there's no preference. But with the trans one, you have this conformer where they're both equatorial. So that's going to be the preferred conformer versus the one where they're diaxial. So I say everyone's favorite pastime. When I was in graduate school, my advisor said, if you're bored in seminar, draw chairs, draw them in different perspectives. And then that helps you, aside from using the model kit, it helps you understand or visualize these things. So on Wednesday, we'll continue on where we're going to look at these things now with Newman projections to look at the dihedral angles. Is something syn? Is it anti? Is it gauche? And then we'll start stereochemistry as well.